Good morning, everyone. Let's start by getting logged into Clever. All right, so as we get going, let's get this little icebreaker. What's the most embarrassing thing that you've ever done? Yeah, I like to fall a lot, and I feel like that's always really embarrassing. I also sneeze funny, and people make fun of me. Anyway, welcome to week 8, live lesson 15. We are moving into our next unit where we're continuing with this storyline and thinking about how matter is created. But now we're starting to think about wait, what the heck is matter? What are the parts of matter? Some reminders grades have to be posted by Wednesday at 3. So please make sure that you are doing your best to get caught up on all assignments. Um, Included in that is everything up to the Unit 1 assessment. Now, if you haven't done the Unit 1 assessment, that is also really important for you to get done. But that is not going to be included in your first 6-week grades. Okay. Other things, continue to check for comments, look at your grades, check for questions, check your Edpuzzle that those are going all the way through. I've had a couple people tell me that they did the Edpuzzle, but every time that I go to check their grade on Google Classroom, it doesn't show that they've done it. So please make sure that you're watching the Edpuzzle all the way through. Remember, our expectations in all facets of this digital virtual classroom is to be safe, responsible, respectful, prepared, and here. Remember our live lesson expectations. I really hope to see you at the next one. And as always, thank you for your hard work. Show yourself some appreciation and some self-love too, because you're doing a really great job. So this week we are on week 8. And again, we're thinking more and deeper at what's going on during nuclear reactions and what are atoms and what are the parts of them. So today you have a couple of assignments. One was actually posted yesterday based on your assessment scores. The next one, or the assignment for the lesson, I'll explain at the end of the lesson. The remediation or extension activity, again, was based on your grade on the test. This is a way for you to make up points that you might miss on the test. So it technically is an extra credit assignment. You either get the Big Bang Cami, so that's using a new application that allows you to annotate and draw within a text. So the text is about the Big Bang, and it's called Sketch to Stretch. You sketch things that make you think of or remind you of or connect to each chunk of the text. The extension activity is to view a portion of a documentary called Particle Fever that discusses the really cool scientific exploration of figuring out what the moments after the Big Bang were like using a Hadron Collider and the discovery of what is called the Higgs boson. So you'll have one of those two. And again, this is extra credit. Several people have asked for extra credit. Here's your chance. So tell me, how did the assessment go? Great. So most people thought the multiple choice was pretty easy, and our scores kind of represent it, that they're near. I told you it's embarrassing. Whew. Most of the scores I think our average is about an 8 out of 10 because of those 2 bonus questions. So that's really awesome. The CER is definitely more challenging, and it's meant to be more challenging. But if you watched the recorded lesson or were in the live lesson where we went through what the process looked like, most people thought it was pretty okay. So this new unit that we're talking about is called periodicity. And essentially what that means is like, what are the elements that make up matter? And we have to start by going back to the previous unit where we talk about fusion in stars. So I want you guys to tell me as we watch this short video, think about how do stars form, how and when does fusion occur, how much energy is involved, and what is produced in nuclear fusion. So this video was written by Stephen Hawking, who is a recently deceased astrophysicist who has been really influential in figuring out what the beginning of the universe looked like and how we have gotten to this point now. So again, thinking about those 4 questions as we view this.
13.5 billion years ago, the universe was mostly hydrogen gas, with gravity doing what gravity does, which is to slowly pull it into vast clouds. Hydrogen is the simplest of gases, but it has a very special property. It's a tremendous source of power. Heat hydrogen to around 10 million degrees and it begins to produce the energy that makes the stars shine and supplies the universe with warmth and light. To see how this works, let's imagine we could make a small star here on Earth. First, we need plenty of hydrogen gas. About a sports stadium full would be perfect. Next, we need to imagine squishing this hydrogen together, just as gravity does in space. As the hydrogen compacts, the atoms of gas start bouncing off each other, and the temperature begins to rise. By the time it's compressed down to the size of a soccer ball, the hydrogen reaches the critical 10 million degrees, and a process called nuclear fusion begins. The hydrogen starts to fuse together, making a new, heavier material, helium. With every step of this tiny bump and grind, some matter gets converted into pure energy. We have created a miniature star. Of course, if this was a real experiment, you wouldn't want to go anywhere near it. The energy given off, even from a star this small, would be devastating. Back in the early universe, the same process happened for the first time on a much, much bigger scale. Gravity compressed the hydrogen gas clouds over millions of years until deep in the center, the hydrogen became hot enough for fusion to occur. The first star burst into life, pouring its energy into the vast universe. A product of the laws of nature and the raw materials left over from the Big Bang. It was almost 1,000 times bigger than our own sun and burnt a deep blue. What's more, this star soon had company. The stars were turning on. This same process still happens in our sun, which is where we get the energy we need to live.
All right. So, answer 2 of these. How do stars form? How much energy is involved? How and where does nuclear fusion occur? Or what is produced in nuclear fusion? Answer 2 of these. So, nuclear fusion, as was explained in that video, is the process of bringing together 2 smaller nuclei to combine and form a larger nuclei. When this occurs, crazy tons of energy is released. Now, nuclear fusion can't just happen to any 2 atoms coming together. They have to have intense heat, pressure, and gravity pulling them together, which is why it happens most often in stars. This process creates larger elements than hydrogen, because hydrogen is like the first one that would come together. And you have to have a special type of star called a supernova to form the really heavy stuff. Now, if we were in class together, we would be doing a modeling exercise to show um, what we mean and what the forces are that are at play when we're thinking of fusing two atoms together. So, a nucleus is a positively charged object. And we're going to learn about what that means and why it is actually later this week. So, we think of those two positively charged nuclei like magnets, okay? So magnets we know have a north and a south end. It's called the North and the South Pole. If they are opposites facing each other, what happens? The magnets are pulled and drawn together. But if you flip them and you have the same poles facing each other, what you find is that they actually are repulsed and push away from each other. So these two nuclei have the same charge. Similar things are repulsed. They do not want to come together like things come together. So, as is shown over here in this GIF on the left, the positively charged nuclei don't really want to come together, but they have to get close enough with high temperatures and high speeds that the force of the nuclear force that wants to bring them together overcomes this repulsive force that pushes them apart. And again, we would do this with a magnet demo, showing how the nuclei don't want to come together because they're similarly charged. But with an outside force, a nuclear force, and gravity pulling them together, they are able to stick together and fuse together. So those three major forces are gravitational. Those are forces inside of the star that are pulling particles together. The electrical force is what pushes them apart. And then the nuclear force is what ultimately is wanting these two atoms to come together. These two nuclei come together to form a larger atom. Okay, and where's the only place where there's enough heat and pressure to really overcome these repulsive forces? It's in the stars, right? Those are the only places where there's enough gravitational force as well as just heat that is allowing these particles to come together to form a larger. Now, let's view this. What do you see and observe going on in this GIF? What do you see? What do you observe? So what we are observing is a nuclear bomb. And most nuclear bombs, as well as most nuclear reactors in power plants, use what is called nuclear fission. So fission is kind of the opposite of fusion. Fusion is when you're bringing two atoms together. Fission is when you're splitting a larger atom apart. And the splitting occurs because you have an unstable, or what we will call a radioactive element to start. That means that it's on the edge as is, and all it takes is a little something for that split to occur. All right. There is massive amounts of energy that are released, as well as you'll get two smaller atoms. That makes sense. If you have something big and you split apart, it's going to make smaller products, right? Now, this is a whole lot easier to recreate and to kind of facilitate happening than what's going on inside of a star. So that's why fission is most often used in nuclear bombs as well as power stations, so power plants. Now, one of the things that is an issue with these nuclear fission reactions is that they produce a ton of radioactive material. And radioactive material it's just one of the products, is that when you have this radioactive substance, when it splits, it releases this radioactive material. And ideally, it is able to be collected and is not able to cause any damage. But sometimes, even just the small amounts actually are harmful. So radiation comes in multiple forms, like light is radiation, but one of the products of nuclear fission is actually what are called gamma rays, and that is a super harmful type of radiation because it goes through your whole body and is incredibly damaging to your DNA. And when you have high levels of radiation over time, it can cause some serious damage to your body. And so this chart over here shows some of the things that that can happen. So that's why you are only supposed to have so many CT scans or X rays a year, right? It's not unlimited because it can cause damage. That's why if you are in the sun over too long of a time and get sunburned, it can cause cancer of the skin, right? It's just a really radiation is a really dangerous thing that can kill your cells and and damage your DNA. All right, so to finish things out, we're going to watch one last short video, and I really want you to be thinking about how are these two processes similar and different from each other.
Fusion and fission are cousins, the yin and yang of nuclear physics. Both turn matter into energy using the most famous equation in all of science, E equals mc squared. The equation tells us that matter can turn into energy, and when it does, it gets multiplied by the speed of light squared, a very big number. Both fusion and fission convert a little bit of matter into a lot of energy, so how do they differ? Fission means to come apart. Imagine a tablet of Alka-Seltzer dissolving in a glass of water. Fusion happens when atoms come together, when two become one. In both cases, we end up with a little less mass than what we started with. That missing mass multiplies by c squared to become E. In fission, the fizzing happens on its own. Radioactive elements such as uranium and plutonium split apart without any prodding from us. This makes fission relatively easy to control. It's why it's used in all existing nuclear power plants. Unfortunately, the stuff that uranium and plutonium fizzes into is toxic and radioactive, creating the byproduct that we call nuclear waste. Fusion is cleaner and more powerful, but it's much more difficult to achieve. It requires slamming hydrogen ions together with such incredible violence that they overcome the repulsive forces pushing them apart. As a result, they fuse into helium. Today, fusion only happens in places with incredible temperatures and pressures, like the center of the sun or a hydrogen bomb. But scientists are trying to squeeze hydrogen atoms together with powerful magnetic fields or laser beams, allowing us to control the fusion reaction and extract its energy. Yet all this squeezing takes a lot of energy, much more than we've been able to get out of the process. Because of this, the first fusion power plants are decades, if not centuries away. Until then, fission has the only mc squared we'll be able to use for energy.
All right, so tell me something about fission, tell me something about fusion, and tell me something they both have in common. All right, so you guys are going to be, your assignment for this week is going to have you participate in a small group discussion on a Padlet. And I know it's weird because, like, you obviously can't talk to each other in person, and you're maybe going to be doing it all at different times. But the way that this is going to work is I've made 3 different Padlets for 3 different groups. There are questions listed at the top. Make sure you scroll all the way over to find all of them. You're going to be asked to engage in the Padlet 3 times, okay? At least 3. You can do more than 3, but at least 3 times. Either answering a question or answering or responding to a classmate's answer, okay? Now, you can do this you need to do this in a couple ways. I don't want you just typing all of your responses. I really want you to try and engage deeper than that. You can have one typed one, but I need you to have at least one recorded video or voice answer, and at least one that includes some sort of picture or video or website or some link to another source, okay? Now, if you're like, I don't know how to answer any of these questions, I didn't get this, I attached this slideshow to help provide a resource and to help you answer some of them, as well as a really short reading that also will cover all of those questions and what is being asked of you. Okay. Again, to show you what this looks like, we'll go to Padlet. Again, you will have just a link in your Google Classroom. You'll open this up, and the Padlet has these questions for you to answer. Again, responding with text, a link, a photo, and then for one of them, you need to have a film or a voice recording as well. Okay. So that is it for today. Please make sure again that you're doing that remediation or extension for extra credit and that you are participating in the Padlet discussion. Thanks, guys. Have a great week, and I will see you at the next lesson. Bye.